Hi, and welcome to a geometry video brought to you by the Answer series. In this video, we are going to continue working with circle geometry, and we are going to have a brief look at the midpoint theorem. The midpoint theorem packs a punch. So if we have a quick look, midpoints P and Q are given, and in this situation, if we join the midpoints up, we get PQ, and the length of PQ will always be exactly half the length of BC. In addition, PQ will be parallel to BC. As we've been discussing, if you do anything in geometry, you should be able to justify it. So we're not going to accept this theorem without having a quick look at why it works. We take the triangle that we were given, triangle ABC, and we start by joining up the midpoints the way we've just done. And we then continue, after we've joined up P and Q, we continue the exact same length from P to Q as Q to R. In other words, Q is the midpoint of the line PR. Now, taking that quadrilateral that we've just created, if we trace it, we have APCR. This quadrilateral is special because the diagonals bisect each other, so we know that we have a parallelogram. Based on that, we can make a few claims that are very important. RC is going to equal AP because they are opposite sides of a parallelogram. And because AP is already equal to PB, we know that the line RC on the far right here is equal in length to the line PB. We also know that RC is parallel to AP because we have a parallelogram, but because AB is a straight line, it means that PB must also be parallel to RC. PB, CR, is a parallelogram because the opposite sides PB and RC are both equal and parallel. We can explain that PR is equal to BC because they're opposite sides of the parallelogram, and we can claim that PR is parallel to BC for the same reason, opposite sides of the parallelogram. But PQ, by construction, is half the length of PR. We've also proved that PR and BC are equal, so we can substitute PR with BC, and we've now proved that PQ is half of BC. If you use the midpoint theorem, you simply have to state midpoint theorem. So if, for example, I give you a length here of 5, and I ask you to calculate the distance from B to C, or the length of BC, all you would have to do is say BC is equal to 10, and your reason would be midpoint theorem. So in any context, as long as you have midpoints on both sides of a triangle, the line joining the midpoints will always be half of the third side of that triangle, in this case BC. In example 1, we are going to start by processing the given information. O is the center of the circle. We know that LOM is the diameter of the circle, and it doesn't help to just mark things off. So think about what you're marking. A diameter always subtends a right angle. We may or may not use that, but it's important to note it. They're telling us that we have another line, ON, which is a bisector of chord LP. So if we go back here, the line ON bisects the chord. So this chord LP is bisected, and that means we know that we have right angles if we need them. PM equals MS, very valuable information because equal chords subtend equal angles. So without even being asked to find this, we're noting for ourselves that those two angles are equal because they are being subtended by equal chords. Finally, we check that the angle that we are given of 31 degrees is actually indicated on the sketch. Now we are ready to answer the questions. In question 1.1, we are asked to find the value or the size of angle MOS. So to begin with, we are going to trace the sides that form the angle so that we know where we are working, and we're going to try to find that angle. Now, that angle is at the center of the circle. So we've already been through the first part of our logic. We know what we need to find, and we know where it is on the sketch. What do we know that is helpful? We'll find that out by tracking down. So what we know that is helpful really is that it is subtended by this chord MS. And if we look at our circle theorems, there are circle theorems that use that chord. So we have a chord subtending an angle at the center. And if we look at this theorem, it works very nicely in this question because joining chord to angle T creates an angle on the circle edge, and the angle at the center of the circle is always twice the angle on the circumference. So if we know that angle T is 31 degrees, then we know that angle O is 62 degrees. Angle MOS is 62 degrees. Angle at center is equal to twice angle at circumference. In 1.1b, we are finding the size of angle L, and angle L is being formed by two lines, so we're going to trace them. When we do that, we realize that they are both going back to form a chord, which is PM, and chord PM is equal in length to chord MS. That means that the angle subtended by MS, which is at T, is equal to the angle subtended at L. So angle L is 31 degrees because equal chords subtend equal angles. Written up neatly, we simply claim that angle L equals 31 degrees, equal chords, equal angles. In question 1.2, we need to prove that ON is half the length of MS, and this is the reason why we went through the midpoint theorem earlier in this video. So if we look carefully at the information we've been given, ON is a line that joins two midpoints because we know that LM is a diameter, so we can confidently mark off LO equal to OM because we have a midpoint. We've also been given that N is the midpoint of the line LP, so we clearly have two midpoints being joined by the line NO. What that does is give us a relationship with the line PM. NO is a half of the length of PM. Now this might feel wrong because we're not even being asked to work with PM, but remember that they've told us that PM is the same length as MS. So if we know that NO is a half of PM, then we also know that it is a half of MS. Looked very difficult, but because of the midpoint theorem, it's very easy. So if we write that up properly, we're going to start by acknowledging that we have midpoints. So N and O are midpoints of LP and LM respectively. Then we're going to make the statement ON is a half of PM, midpoint theorem. We explain that PM is the same value as MS, and then we swap in the MS in place of PM, and we have our result. ON is a half of MS. That is a 4-mark question, and if you think that through, it is a really easy 4 marks if you know what you're doing. In example 2, we have to reset. So you can't take everything that you're thinking from example 1 into example 2 because it is a new question. So slow yourself down a little bit, reprocess. O is the center of the circle, mark it off on the sketch. KOM bisects a chord, and we have a given angle. So let's take that in 2 parts. KOM bisects a chord, so this line coming down here will in fact be perpendicular to that line. So we know that this angle is 90. A line from the center of a circle to the midpoint of the chord will always create a right angle. In addition, we need to make sure that we go into the sketch and check that they have indicated the angle of MNO as 26 degrees. Finally, we are going to process one more angle. Angle NKP is indicated on the sketch, and everything else we will figure out as we go. So we know what the gist is of the information we've been given. In question 2.1, we are asked to determine with reasons the size of angle O2. We're going to start by locating that on the sketch. Angle O2 is an angle at the center. If we trace the sides that form the angle, it does help us to engage properly with the question. So those are the sides forming the angle. They are coming off an invisible chord, PN. PN subtends an angle which we can see at K, so there's a relationship between those two angles. And all we have to do is recognize that the angle at the center is twice the size of the angle on the circumference. So angle O2 will be 64 degrees. To write that up, we simply claim that angle O2 is 64 degrees, and our reason to justify what we said, angle at center equals twice angle at circumference. In question 2.1, we are still working in the vicinity of point O, but this time we need to find the size of angle O1. So as before, we're going to trace back and see where the angle is. We know what we need to find, but sometimes that isn't kickstarting our process enough. We know where it is on the sketch. What we need to think about now is, what do we know that might be helpful? And if we find out something helpful, how are we going to justify our answer? So we need to really think this question through. We can't use the radii, and the temptation here is to just go into this triangle on the left. But because you don't know the size of angle K2, if you try that, you're going to get stuck. So you have to try. When you get something not working, just take it out and say to yourself, that's not the right approach, let's try again. All right, so now we need to look at this from a different perspective. So we've got to ask ourselves, why are they giving us the 26-degree angle? Why did they tell us this was a midpoint? Maybe that's relevant to the question. So if you extend the line from O to M, and then from M to N, and then go one step further and put that extra line in, you know that angle M2 is 90 because the line from the center to the midpoint of the chord will meet it perpendicularly. That means that we can find angle O1 in two different ways. We can either take this arc, extend it across the 64 degrees, which we know, and use the exterior angle of the triangle. It gives us an answer in very few steps. So angle KON is equal to the sum of the two interior opposite angles. So angle KON, very simply, is equal to 116 degrees using the exterior angle. If we subtract the 64 degrees, which we've been given here, then we will be able to work out the size of angle O1. There's often an alternative method. It's pretty straightforward to find that third angle in the triangle. So if we do the arithmetic, this angle will come out as 64 degrees. And if we have that angle and we have the angle here of 64 degrees, then we have two angles that add up to 128 degrees. So we can find angle O1 by a second method using the angles on the triangle and then the angles on the straight line. So as long as you engage with the question, you can come at it from different perspectives and solve it in a number of different ways. If we look at the solution written up very nicely for you, we have angle O1 and angle O2 being combined to form the sum of 26 and M2, because we're using the exterior angle of the triangle. Angle M2 we can account for because we've got the line from the center to the midpoint of the chord, so we know it's 90 degrees. We also know that angle ONM, this little angle here, is 26 degrees. So by using simple arithmetic, we can conclude that angle O1 is 52 degrees. If we use the second method, which doesn't use the exterior angle, it will require more steps, but it's a safe method. So we can start with angle M2 being 90, line from center to midpoint chord. We can explain that O3 is 64 because we have the angle sum of the triangle. Angle O1 is going to equal 52 degrees because the angles on a straight line add up to 180 degrees. In 2.2, we are doing a proof. So we have to think a little bit more carefully because it isn't just about the answer, it's about how we justify the answer. So Kn bisects. So let's find the line Kn and let's trace it so that we can see what we're working with. So this is the line Kn. Now that line bisects angle OKP. So start at O and create the angle that they were talking about. There's angle OKP. All right, now we have a better idea of what we're working with. We also know that the angle at K2 is going to end up being 32 degrees, because if it isn't 32 degrees, then we don't have a bisector. We have to find that value without any reference to Kn. So we have to look at the picture and ask ourselves, what do we know that could be helpful in this context? And what jumps out at me is that I have a radius right here next to the angle I'm interested in, and another radius. If I trace the line ON, I have a second radius, which means I've got an isosceles triangle. Now, this 64 is confusing because it's only part of the angle, whereas the 116 is the whole angle. So always make sure that if your sketch has become confusing, that you find a way to make it easier to work with. All right, so now all I have to do is work out the angle sum in the triangle, and I already know that this angle here will have to be 32 degrees because everything will balance. So now what I need to do is just find a short, easy way to explain that to somebody else. We need to write up the solution. It is 3 marks, so we don't have to write a lot down, just what is essential to somebody to know that we know what we are doing. So we're going to tell them that K2 is equal to angle KNO. For us to understand that, we can have another quick look at the sketch. We have an isosceles triangle, so we know that the angles opposite the radii are equal, and that's all we're going to write down. We know that the angle at O, this very big angle, is 116 degrees. So without having to show the calculation, the balance to get to 180 is 64, and so each half of that is 32. So all we need to write down is 32 degrees, angle sum triangle. We don't have to mention that we're working in triangle KON, but it is easier for somebody else to follow our solution. The final conclusion is essential. KN bisects angle OKP. If we look at the second option very briefly, it is an option to find angle O3 equal to 64 degrees. So in the sketch, we would know the 64 degree angle. And then we could simply use the exterior relationship. So those two interior opposite angles would each then be equal to 32 degrees. So that is an alternative if you prefer.
Check out the video description below for practice questions from our study guides. If you found this video useful, give it a like and subscribe to our channel so you don't miss any new episodes. Follow us on Instagram or Facebook to stay on top of the latest TAS news and launches. So that's it for now from the Answer Series, your key to exam success.